looking at this chapter so far, what have we done? We did work as FD cosine theta, right? Now, if the angle is 0 degrees, that means if you're doing it like that, that means it's FD. You can have a positive work and a negative work, so you know that expression. And we also studied kinetic energy. So when you do work, it transfers into kinetic energy, half mv squared. We also did GPE, which is mg times the change in height. And we also did EPE, which is the elastic potential energy, half kx squared, where k is a force constant coming in from Hooke's law. We also did power as work over time or energy over time. And we also did power as force times velocity, right? Yes? Yeah. Did we talk about it? Did you come up with this equation? Power is FV? No. Yeah, we didn't? Okay. It's not a totally new expression. You can look at this right now. Power is work done over time, right? And what is work done? Force times displacement over time. And what is displacement over time? Velocity, that's what it is. That means if you're dragging something, applying a certain force, and making it go at a constant velocity, how much power is involved? It is just the force times velocity. Like your car. Your car, from friction, there's a driving force applied on the car, right? And if the car is actually coasting at a constant speed, constant velocity, how much is the power supplied by the driving force? It is the force times how fast. You get it? That's a power supply. So yeah, this expression is coming straight away from the work done over time. The force times velocity is also power, so you may have to use it somewhere. Okay. And then we talked about energy conservation, where energy lost is definitely going to be accountable. So if energy is being, lost in one form, it has to go to some other form. So that means energy cannot be created nor destroyed. It can only be changed from one form to another. That is energy conservation. So we have done, this is the entire chapter. And we are done with the chapter. And we did a couple of questions, right? And using these concepts, only these concepts, you should be able to solve problems. So let's solve some problems. And every problem is going to be unique. Every problem requires you to think in a new manner. Don't think of memorizing these. Of course, there is nothing here. What equations are these? The equation is not the major thing. Don't memorize any of these equations and try to use them straight away into problems. Instead, what do you do?
You think about the
situation,
yeah.
And then draw a diagram, right? So the words in the problem, with all my experience, even now, if I'm given a new problem, I look at the problem and I won't just stare at the problem and then start solving it straight away. Instead of that, what I do is I convert that verbal problem into a picture problem. In other words, read it, translate that information into a picture, put all the numbers and stuff like that you know over there. And then after that, I will not look at the problem anymore. I'll be looking at just that picture and getting a better imagination going on there. And then after that, I look into it and say, all right, now what physics can I apply? Should I use equations of motion? Should I use energy? Should I use this? Should I use that? Different forms of problem solving. It's not like one method always. And once you look at the picture, you'll get some extra clues. You'll say, oh, the velocity is 0 there. Oh, this is this there. You'll get extra ideas. And then once all those ideas pop up, then you say, okay, what physics is coming in? So what equations can I involve? into the problem, and then after that, set it up, solve for unknowns. Okay, once you solve for unknowns, your problem's over. So you cannot just search for one equation to start off. Okay. I'm going to start solving some problems over here, and then we'll see how it goes. Now, if I had asked you this question earlier, you would have done it a different way. Here's the question. A football player throws the ball at a velocity of 20 meters per second at an unknown angle. Okay, so the ball goes 20 meters per second velocity at an unknown angle. And what is given to you in the problem is, you know what happens, right? Projectile motion, right? The ball goes like that. What's given to you is that its highest point is 15 meters. You know, the highest point of its trajectory is 15 meters. Question is, how fast is it moving here? Is it moving at all? At the highest point? Yeah. So how fast is it moving? The question is only that much. A football player throws a ball at 20 meters per second at some angle, and the ball goes at the highest point of its trajectory. It is 15 meters above the ground. Question is, how fast is it moving there? Problem. Now, if you're thinking of using one of these equations straight away or using anything, you cannot do it. Now, 2 months back, if I had asked the same question when we were doing chapter 3, what you would have done? What have you done? Resolve this into 2 components, right? You'll split it into, what is this? 20 what? 20 cosine theta, and this one? 20 sine theta. And then after that, you'll set up a table, right? Horizontal, vertical, and then put all those things down, and you'll look for some clue of using equations of motion. And then once you get some equations on the left-hand side and right-hand side, you will look at them and say, all right, can I substitute here, there? You know, you're trying to solve problems. That's what you would have done. What can you do now differently, because you have come up with this problem and you can solve this problem in a different style, not projectile motion method. How else can you solve this? Anybody has any ideas?
You can use the equation velocity equals the square root of 2gh.
Velocity equal to square root of 2gh. That won't work quite, because there you're just transferring one form of energy to the other form, right? But now here we have to think a little more in a deeper manner. Okay, what kind of energy does it have over here? This is a line of thought that you're supposed to have. What kind of energy does it have here when you're throwing the ball, as the ball is going off? It has kinetic energy, right? And GPE, with respect to the floor, the GPE is how much? 0. So no GPE, correct? Now what kind of energy does it have over here? It has GPE, yes, it has GPE, and does it have kinetic energy? Yes, because it's still moving. It has kinetic energy because it's moving. So now which kinetic energy is bigger? The first one. So this one is definitely bigger than this. So the 2 kinetic energies are different, right? The reason is because here is 20 meters per second and there is something V. We don't know. So the velocity over here is definitely smaller than 20. That much is very sure. What do you do now? Use energy conservation. What is energy conservation? Energy cannot be destroyed or created. It can only be changed from one form to other forms. So the total energy here and the total energy here should be
K1.
the same. So basically what you should be doing is K1 is GPE plus KE2. That is your main concept to be applied here. And what do you do now? Substitute. Half M. You know the mass of the ball? No. So M. 20 squared. Now you're substituting the equations. What is GPE? Formula? MG. So M, we don't know. G, yes, you know. H, 15. And then what is the kinetic energy? Half M V squared. We don't know the V. So leave all that there. Is there any way to, simplify this and solve it from here? You can eliminate the mass by dividing throughout by mass. So divide the whole thing with mass, then you get this knocked off. Rewrite the expression once again without the mass. 20 squared is 400. 400 divided by 2 is 200. Is equal to 9.8 times 15 is
147.
147. That's it. Nothing more there. Plus v squared over 2. Now is that solvable?
Yes.
Okay. How much is v? 10.3 meters per second. See how fast we solved it. It would have taken one full period if you were actually doing with projectile motion. Because you know what, angle is not given to you, so you'll have a lot of headache in solving it. So this could be a very tough question if you were asked the same question in projectile motions chapter. But using energy method, you got the answer. So most of the time the energy method will be faster than the other methods. Most of the time.
On the midterm, will we have independence on using whatever method we want if we were asked a question?
You can do whatever you want. Yeah. That's why I said most of the time they first try to use energy method. If that doesn't really, feel comfortable, then go to the equations of motion. Energy method is much easier instead of using equations of motion. So what we did over here is simple. The energy here is equal to the energy there, and then just equated it, divide by mass, mass gone, so you don't have to worry about it, and then finally you have 10.3 meters per second. Any questions on this? Good. Now if my second question is, find theta. My second question is, what is the angle theta? Find it out. How can you do it? Let me see if you have any ideas. Is there any way to find out the angle theta? Solve it. Yes?
Could you use W equals F equals M?
No. That won't help because that one is completely a different concept. That one is like if you're applying a force at an angle and displace it, you do that much work. Here the angle is not constant, right? The angle is theta only in the beginning and after that it's changed. So you can't do that. Anyone has any answers? You should have solved by now. With the knowledge that you have already, you should have solved it. You have the knowledge to solve it. The only thing is it's not clicking, that's all. It's not just clicking. You can answer this question in no time. What is the angle theta? You have learned the concepts to solve that earlier. If anyone has the answer, just raise your hand and then tell me what it is. No one has the answer? How do you get the angle from this picture? Yes?
What would be 20 cosine theta is equal to 1/2 and
20 cosine theta is equal to what? Why?
Because K.
20 cosine theta is just a force. How can you equate force with energy? Yes. Seems to have an idea. Yes.
Well, I'm just thinking.
Yes. You have an idea? Looks like. Yeah.
20 is to use the power equals force times velocity.
Because the velocity is not change. Is not a constant, so you can't do that. That is only for force times velocity if the velocity is constant. You can't use it otherwise. Any other ideas? I said it's very simple. You know, you should be knowing how to tackle that puzzle. You have to look for clues, and once you look for the clue, you'll just pounce on it and solve it.
Do some trigonometry.
Well, that is what some students will normally think about, but trigonometry cannot be applied here because this angle is, if it was a steady angle like that, and if that was 15, yes, you could have done trigonometry. But yes, what you said is also right. You're going to use a little trigonometry. Yes, we are using trigonometry. There we go. Yep.
What?
You know what? When you resolve this velocity into two components, what is this component? 20? And what is this? And you know the horizontal velocity will never change, right? The vertical velocity will change because of gravity, but the horizontal velocity should stay 20 cosine theta, 20 cosine theta, 20 cosine theta. What is the speed here? That's it. Good. 20 cosine theta is 10.3. So all you do is 20 cosine theta is 10.3. So what is cosine theta? It is 10.3 over 20. Get the angle theta from there. 59 degrees. Now see how the problem is tackled? You don't do too much work, but you have to really think everywhere. Yeah, that's why I said you got the ideas. It's a matter of just implementing it. You know, just bring it and use it. You have the idea. You already know in projectile motion the horizontal component never changes. And at the topmost point of its trajectory, it has only one component, which is the horizontal component, 20 cosine theta. That's it. Okay? I'm going to read some problems from here, from the textbook, from your e-text, and we'll solve. I want everyone to be actively doing it. I'll read the question, maybe I'll draw the diagrams as well slowly, but start working. So the problem that we just did, if you were tackling it only by projectile motion, it would take real time to kind of, and a lot of equations to mess up with. Ultimately, you can solve for the angle theta and the velocity on the top. It's all possible, but it will be a lot of work. But using energy method, it was like straightforward. Okay? All right, here is a question. A 1,300 Newton crate rests on the floor. Now, what is the meaning of the term a 1,300 Newton crate? The weight. Now, if instead it was 1,300 kilogram crate, we're talking about its mass. You get it? So the quantity that is given to you, the data that is given to you will tell you what it is. Straight away, the unit will be telling you what it is. A 1,300 Newton crate rests on the floor. How much work is required to move it at constant speed? 4 meters along the floor So I'm drawing it again here. A 1,300 Newton crate sitting on the floor. How much work is required to move it at constant speed 4 meters along the floor against a friction force of 230 newtons? So there is a frictional force of 230 newtons, and you are dragging this one 4 meters forward at constant speed. At constant speed. Question is, how much work is done? So how much work is needed to drag this 4 meters at constant speed? Yeah. What do you do? Whatever I read, I put it on picture format. I'll read it again. A 1,300 Newton crate rests on the floor. How much work is required to move it at constant speed 4 meters along the floor against a friction force of 230 newtons? Is all the information on the diagram? Yeah. Once all the information on the diagram, now focus on the diagram and answer the question. What can you do now here? How do you tackle this? How do you find the work done? Huh? Draw the forces, okay? Which forces?
Gravitation.
Okay. Gravitational force is here, 1,300. Then,
force?
huh?
Normal force?
Normal force is same thing, okay.
You're pulling it, right?
You're pulling it, okay. What force are you pulling it with?
You don't know, yeah.
You know it.
Well, is at a constant speed.
Yes, so,
So the force would be its mass. Or no.
Is it plus?
Well, yeah.
uh-huh.
It should be 230.
It should be 230.
Right.
You know why? Why should that force be 230? It's something that you interpret from the problem.
You have to. You have to do it.
Because if you're moving something at constant speed as per Newton's first law, the net force on the object should be 0, which means if there's a friction of 230, you must have a force of 230 to keep it coasting at constant velocity. You get it?
Yeah.
So you discovered it's 230 and you're moving it 4 meters. How much work? What's the work done? Since you're moving it in the same direction as the 4 meters, just apply that. How much? 920 joules. That's all. That's all. All you have to do is that much work. The second part of the same question says, how much work is required to move it at constant speed 4 meters vertically? 4 meters vertically. You're going to move it from here to here. 4 meters vertically. At constant speed, that way. How much work is required to be done? Ideas?
The upward force you apply should be at least 1,300 newtons.
The upward force that you need to apply should be 1,300 Newton exactly. Why? Because the downward force is 1,300 is weight. So you need to apply 1,300 exactly for it to move at constant speed. Because if you apply anything more than this, it is supposed to be accelerating. Correct? Griffin, okay? 1,300 is the max, is the force required to make it go at constant speed. So what's the work done? 5,200 joules, that's right. 5,200 joules. Do you get the whole problem? Clear? That's simply work done. We are just using the term work done to get it. Next question. How much work did the movers do horizontally? How much work did the movers do horizontally? How how much work did the movers do horizontally, pushing a 160 kilogram crate 10.3 meters across a rough floor without acceleration? So now it's a 160 kilogram crate. They're pushing it on a rough floor, and they're moving it 10.3 meters. And they're pushing it across a rough floor without acceleration. And they said the coefficient of friction is 0.5. So they gave you the coefficient of friction is 0.5 and no acceleration, which means at constant speed. And they're pushing it with a force. So the problem is all on the board. The workers are pushing this crate from here 10.3 meters away, and they're working against the forces of friction. And they are making it go without an acceleration, which means at constant speed. So without an acceleration means you apply a force just enough for it to keep coasting. See, this is without acceleration. I'm not accelerating it. So the force I'm applying should be accordingly. So can you find this force? Is there a way to find that force?
Yes. 700.
How do you do it?
I found normal reaction.
You find the normal reaction. How much?
1,568.
1,568 newtons? Yeah, that's a normal reaction. And the friction that is coming in is mu k times normal reaction. So use that and find out, yes. So it will be 0.5 times 1,568. So we have learned the concept of friction. So we are applying that here. So that becomes 784 newtons. So the friction is 784 newtons, and to move it without an acceleration, what force is required? 784. So we need 784, and the displacement is 10.3. Find the work done.
Which is 8,070 joules.
Yeah.
Or 8,075.
8,075 joules. So the workers must apply that much work. Next question. Start imagination as soon as I start reading it. A box of mass 5 kilogram is accelerated from rest across a floor at a rate of 2 meters per second square for 7 seconds. A box of mass 5 kilograms is accelerated from rest. See, I'm putting the data immediately, whatever you know from the words, yeah.
Wait, did you multiply by the length every time when you convert to joules?
Yeah, force times displacement. VI is 0 because they said it from rest. And it is accelerated at 2 meters per second squared. And it is made to go like that. Let's read again. A box of mass 5 kilogram is accelerated from rest across the floor at the rate of 2 meters per second for 7 seconds. Time is 7 seconds. Find the net work done on the box. Find the net work done on the box. Right. Start writing. Draw the diagram. Net work done on the box is the question. Net work done on the box. Okay. Draw the diagram. So, question is, what's the net work done? To find the net work done, you need the net force and the displacement, right?
Yes.
Now what's the net force?
10.
10, because it's 5 kilogram mass accelerating at 2, so net force is 10. So we have the net force. Now the next thing you need is a displacement. Is there a way to find the displacement?
Yes.
Equations of motion, finished. Find the displacement, you need this. What equation can you use? X is equal to VIT plus half AT squared. So initial velocity is 0, so that's out. So half times 2 times 7 squared. So displacement is 49 meters. Put out here. And what's an answer? That's all. Over. Next question. Okay. Eight books, each 4.3 centimeters thick. Look at this book. 8 books such as this, 4.3 centimeters thick, with a mass of 1.7 kilograms. Okay? Lie flat on a table. The books are lying flat on the table. How much work is required to stack them one on top of the other? How much work is required to stack these books like that? Huh? 0. No work required? Can a dead man suddenly stack the books like that?
If you move it.
So if no work is required, then anybody can just like get those books to stack up like that by itself.
They have a little amount of gravity.
I'll draw that. So this is 1.7 kilograms each book, and this is 4.3 centimeters thick. And you're stacking the books like that. Question is asking how much work is required to be done. Now, instead of putting all those 4.3s and all that and the mass, I will call it mass M, and this, the thickness is X. Okay? How much energy is required? How much work should you do to put the first book in place? All the books are on the table. To put the first book in place, how much work is required? None. None. For which one? Only for the first book. What about the second book? How much work is required to take the second book and put it up here? Is the second book gaining some energy? What energy? GPE. Because it's gone up to a height, right? How much GPE did the second book gain? mg times? How much height? How much height did the second book go over? Correct? I'm writing in terms of variables so that you'll see why I'm doing it. I don't want to put all the numbers down. Do you get the answer as to why this one is mgx? Because mg is the weight of this. In other words, GPE. How much GPE did this book gain? mgx. What about the third book? How much work is required to put the third book here? mg2x. What about the fourth book? mg3x. What about the last book? mg7x. If you add up all the work, that will be the total work required to stack all those books. Do you understand so far? Good. Now, why I said, Don't put all those numbers 1.73 and all that, 1.7 and all that, because this is easier to tackle. Now watch. Take mgx common. What do you have? 0 plus 1 plus 2 plus 3 plus 7. Right? What is 1 plus 2 plus 3 plus till 7? How much? 28. How did you get it? How did you get that at 28? How did you get 28? You just add, okay, add this then. You're lucky that it was not 100 books. If it was 100 books, what will happen then? You'll keep on 56 plus 57 plus 58 plus 59. You'll be just going on adding. Will you keep doing that?
Maybe. That's all over.
You have done this in math. You're not applying yourself. This is a series. What you do is n into n plus 1 over 2. You have done this. Adding series. So all you do over here is take n, 100, times 101 divided by 2. That's the answer. 7 times 8 divided by 2. What's 7 times 8? You need calculator. 7 times 8
56.
divided by 2. So if you are given a sequence like this, what if I give you till 1000? No problems. You can add them up in no time. 1000 times 1001 divided by 2. That will be the sum of all those series. Alright, haven't you seen this before? Anywhere?
Yes.
You have, okay. Yeah, so these are the times when you actually use them instead of like adding them up individually. This is 8 books. If it was a larger number of books, you'll be adding a lot of times. Okay, so this is mgx times 28. Mass 1.7. Now this is the time you substitute. G 9.8. X, how much is x?
Oh. 0.043.
0.043. Remember, it is given in centimeters. You have to change it to meters. And then times 28. And then that will give you the total work required to stack all those books together.
330.
How much?
330 is what
I don't know. I'm not sure.
Is
That's
20.
Check. What's the total? 28 times this.
Oh, yeah, I got the 20 point.
Is 20.05.
How much?
20.05.
20.05? You get 300.
I think I skipped out 20 decimal spaces.
Okay.
Of the
That looks right. So the amount of energy required to stack all those books together like that in a pile is that much. Now see how much work you have done. Well, you could have made this work horribly big, because if you put everywhere all those numbers and then add all those big things up, it would have been a lot of work. But by using these sequence, it's much easier. Questions about that? The questions arise only when you do the test, right? Next one. What's the minimum work needed to push a 950 kilogram car 810 meters up along a 9-degree incline? So you can see I'm showing you by example. Reading, drawing the picture, then work from the picture. What is the minimum work needed to push a 950 kilogram car 810 meters up along a 9-degree incline? Nine-degree incline. The car, 950 kilograms car, You're moving it 810 meters. What is the work, minimum work required to take the car up there? Ignore friction. They said ignore friction. That should be easy. What's the minimum work required? In other words, just scoot it from here to there. That's it. How much? MGH. Because this car is sitting here idle. No energy, kinetic or potential. Over here it has potential energy, right? How much potential energy is over here? That's it. The potential energy over here is just MGH. You don't want the car to be moving there. That's why they said minimum amount of work required. So how do you find where is the height?
Yeah.
We have to find it out. The height is right there. How do you find the height? H is 810 sine 9. So H is 810 sine 9. And then you work it out and you get the answer. There is a second part for this question says, if there is a friction of 0.25, coefficient of friction of 0.25, then how much work is required to be done? You do that and let me know. If there is a constant friction of 0.25 coefficient, then how much work is required?